Alright guys, so the objective is to give you guys a basic understanding of circuits and electricity. And we can describe electricity as the flow of electrons through a wire. So all that's really happening in a battery is we have a positive cathode and a negative anode. Inside this battery we have a little chemical reaction going on, and then a lot of charge builds up over on the negative side, and then we have a potential difference which we can describe as a voltage. So we denote this battery in a circuit as this symbol here, a circle with a little plus and a minus. So in electron flow, we have electrons moving from negative to positive. So this is what's really happening in the circuit. So as I have drawn here, we see that the current is going this way with electrons moving from out this negative side and into the positive side, creating a loop. What we use for our calculations in circuit is what we call conventional current, which is this positive charge flow here. So we have this positive charge coming from the positive charge terminal going to the negative, which it's incorrect, but most of the time it makes our calculations easier and it's just easier to use. So then we have to describe this moving of charge, and we're going to describe it as current, which is the flow of electrical charge carriers. And the unit for it is amp or coulomb per second. So a big analogy everyone always uses is to think of current like water. So over here, think of this as water moving through a pipe, and this is the top view. So if you have it laying on the ground and you cut up the top. So we're going to think of it like this, and we have this water moving in through this pipe. Now what happens if it hits a resistance? Or what's going to happen? So let's think of it as water getting pushed through a narrow pipe. The pressure is obviously going to increase, and we're going to describe this in a circuit as the resistance. And the unit for resistance is ohm, which can be thought of, which is volt over amp, and is denoted by the symbol here, which is ohm. Alright, so to continue with this analogy of water moving through a pipe, we're going to look at this little pipe system we have up here. And it's not really that obvious to see, but we're saying this guy here is pretty narrow, and this guy's a decent bit wider. And it's going to want to go the easiest way, obviously. So the water's going to want to go wherever there's the least amount of impedance, or there's going to be the least amount of pressure. And current going through resistors is no different. So I redrew this, but as a circuit. And we have 5 amps with the option to go through the 20 ohm resistor or the 10 ohm resistor. And what we'll see is that more of the current is going to go through this 10 ohm resistor. Why? It's less resistance, it's easier. And we have a formula for this, which is current division. So current through this side up here, I1, is equal to resistance 2, 10 ohm, divided by R1 plus R2 multiplied times the current. So we have our current of 5 amps here, and going into the resistors, and we're able to figure out what the current division is in this top part of the circuit. So if we do our calculations here, we use the opposite resistor, and we get 10 ohms over 10 ohm plus 20 ohm, which gives us a 1/3 ratio. So 1/3 of the current is going up to this 20 ohm resistor versus 2/3 of it is going downward. So now if we want to get our total current on this side, we multiply times our source amperage, which is 5 amps. So we'll end up getting 5/3 amps. So now we need a way to describe the voltage, which is just the electric potential. Like I said earlier, you just have charges built on one side and they want to go to the other. So the unit for it though is volt, which is a joule per coulomb. And we can think about, and there's a relationship between what we know so far, this voltage, current, and resistance, which is Ohm's law, which is V equals IR. And I manipulated the equations here for current and resistance, and this lets us do some calculations. So we have this circuit right here with a 5 volt battery and a 10 ohm resistor. And let's say we want to find the current right here in the loop. We can apply V equals IR and manipulate it over to get I equals VR. And we'll see that 5 volts over 10 ohms is half an amp. So we have half an amp moving this direction. In theory, at least. As we know from earlier, it's actually going downward. But for our calculations, it doesn't matter. And no matter where I put this I value at, it's always going to be a half. So the current is always going to be the same in this loop, since there's nowhere for it to split. Now let's look at this circuit I've built down here, and we have 2 resistors this time, so it's not as easy of a question. So the way we're going to think about this is resistors in series add up. So this is considered series. They're all on the same wire. It doesn't split off anywhere. It doesn't split off like up here. So all it is just resistance 1 plus resistance 2 plus resistance 3. So all we have to do here to find the net resistance or resistance equivalent is 10 ohm plus 10 ohm. And if we take our 10 ohm plus 10 ohm, we get 20 ohm. And we can redraw as this circuit down here if we want to. And then with this, we're able to solve for our current again. And it's just the 5 volt divided by 20 ohms, which gives us 1/4 of an amp. So you're probably thinking to yourself, what happens if these resistors are in parallel? So I'll show you what happens. So we have this circuit drawn here, and we have a 5 volt battery connected to 2 10 ohm resistors in parallel. And what we're going to see is that this R1 parallel 2 is equal to R1 times R2 divided by R1 plus R2. So we see that it's 10 times 10, 100, divided by 10 plus 10, 20, which will give us a value of 5 ohms. So now we can kind of see a neat relationship here. If we have a value here, 10 ohm and 10 ohm, and they're the same like they are here, the resistance of the 2 combined is going to be half. So let's say these are 20. Both of them are 20. The resistance equivalent is going to be 10 ohm. And it doesn't matter what number we use as long as it's the same number. So it could even be a fraction or a decimal. So if we have half an ohm here and half an ohm here, the equivalent is going to be 1/4. 1/4 of an ohm. Now if we think about this equation a little more, this equation is telling us that this equivalent resistance is always going to be less than the smallest value. So let's put a 1 ohm resistor here and a 1 million ohm resistor here. What we're going to see is that the equivalent resistance of it is still going to be a little bit less than 1. And as we know from earlier too, there's pretty much going to be absolutely no current going through the million ohm resistor. But once we simplify our circuit here, since we calculated that this is 5 ohm, we can then calculate the current. As we know, I equals V over R, 5 volt divided by 5 ohm equals 1 amp. And here's just if there's more than one resistor. And all resistors here are equal to 9 ohm. So we apply our equation, like up above. You can only do 2 at a time. You can't combine them all at once. And we get a 9/2 ohm and a 9 ohm parallel. So we do our calculations again, and we end up getting that it is equal to 3 ohm. So we can redraw our circuit here and get a 3 volt battery in series with a 3 ohm resistor. And with this, we can apply our equation here and get that the current is equal to 1 amp. And we again see a neat little relationship here, where if it's all the same number, it's going to be that number times 1/3 for 3 resistors. If there's 10 numbers, it's going to be that number times 1/10. It's just a nice little relationship here we have that can make calculations a lot easier a lot of times. Alright guys, so the last thing we're going to talk about today is short circuits. So in the circuit diagram above, we see that we have a wire parallel to our resistor, but it has no resistance. And as we know from earlier, it's going to want to take the easiest path. So we're going to have all of our current go through the wire here. None of it's going to go through the resistor, in theory. Since wires do have a little bit of resistance, it's not technically zero resistance, but for our calculations, we're just going to say that it doesn't exist. And what we can pretty much do then, once we see this short circuit, is just cross out this resistor. So this resistor here isn't here. It's not doing anything. And now let's say we want to see our current of this little thing here. So just a battery. And we know that I equals V over R. But if we take our voltage source divided by 0, we're going to get infinity. So we have infinite current. And this might seem really awesome. It's like, oh, so we can get infinite power or something like that. But what really happens is we just blow up batteries, and it's just not good. So now let's apply this to solve the circuit I have drawn right here. So we're wanting to find voltage, and we have current. And we see we have a short here next to this 10 ohm resistor. So we can say that this 10 ohm resistor doesn't exist. So we can redraw it as this battery with a 5 ohm resistor. And from here we know that our current is 5 amps. And that's not going to change here. It's still going to be 5 amps. And no matter where we look at it, except for right here, it's going to be 5 amps. So we apply Ohm's law, V equals IR. And we get 5 amps times 5 ohms, and we get 25 volts. So that's the voltage. That's what the battery would have to be to get that current. And below I have some practice problems. I'll upload an answer key to the description, so try a couple of those out. Especially take a look at 3, because you'll see that it's going the opposite direction that we normally solve them. But that's it, guys. So please leave a like. It'll help me out. And subscribe to the channel if you haven't yet. Thank you.